Hello and welcome to another Smart Grid System class. In the previous class, we spoke about power flows. We saw some examples and we spoke a little bit about control systems and smart grids as well, different type of uh, monitoring and control systems in smart grid. This week, we're going to speak about SCADA and EMS. Um, so what are SCADA? SCADA is a supervisory control and data acquisition system. It's technically the control system that we have. Imagine if in a smart grid we have a control room, and SCADA is actually the control system for that. It's for data acquisition, situation monitoring, and grid control via some communication channels covering large geographical areas. Some features are having advanced data collection process capabilities, monitor the entire network with an integrated control system, and supervise operations over a variety of devices, and also to send instructions to devices located throughout the system as well. This is a graph of a SCADA with its different components. We have the communications network. Sometimes it could be internet. Sometimes, most of the times, actually, they have their own communication networks as well. We have the RTUs, which are remote terminal units, the PLCs, the measurements and instructions. And also on the other side, we have the centralized supervisory system and our database. And this is actually what a centralized supervisory system, the control system of a SCADA looks like. Now, what is EMS? EMS is the energy management system that we use. It's a computer-aided tool. The software that we have here, what we call it EMS, and it does a bunch of measurements and monitoring, and also uh, data collection and controlling the system. Some key modules of the EMS are the system monitoring system, which is the state estimation we call, and I'll explain more about that. We have the real-time contingency analysis, or RTCAs, and we have the real-time security constrained economic dispatch, or RTSCED. Now, this is a graph of a procedure for real-time operation of an EMS, EMS and power systems. We have the real-time measurements, which could be collected from different sensors, relays, voltage, power, and so on, that we collect from the system. And we collect the measurement in SCADA. And then for the EMS part, the energy management system, we have the state estimation, or the estimate system status. We have the RTCA, or the scan system vulnerabilities, and we have the RTSCED, which corrects the system vulnerabilities. So this part is the EMS system that we have. The RTCA is a real-time contingency analysis, and RTSCED is the real-time security constrained economic dispatch. Now, what is a state estimation? The first part that we have here. So state estimation is the process of assigning a value to an unknown system state variable based on the measurement. Measurements may be redundant and imperfect. It is based on a statistical criterion that evaluates the accuracy of the estimated values of the state variables. The method is to minimize or maximize the selected criterion. It's a widely used criterion to minimize the sum of squares of the difference between the estimated and measured values. And we use least square estimation. So what you have to keep in mind is that power systems are not perfect. They are not ideal. So we have measured values, but there is a difference between the estimated values and the measured values and the real values as well. So we have type of errors, and I'll explain how we put into account those errors in our EMS system. So power system state estimation is actually power system state estimation actually assumes the network topology and parameters are known to the system operator, which again, we have some errors. The goal of the state estimation is to determine the current power system status based on the measurements. And the measurements are from the SCADA system. The measurements that we get from the SCADA system could be the status of the breakers, switches, and lines, the voltage magnitudes, the branch power flows, and the loads and the generator. So how much load and generation that we have at each time. Now, can we directly use the measurements? No, because measurements are subject to error. It could be small, it could be gross. Some measurements are redundant, but may be very different, like when we have conflicting measurements. And measurements may not cover all state variables. And the state estimation can smooth out small random errors and detect gross measurement errors. And sometimes we neglect the small random errors. Now, let's solve an example. I would solve this problem with three or four different examples. So we have a simple DC model based example to illustrate the principles of state estimation. We have two generators here, a 65 megawatt and a 35 megawatt, and the load, which is 100 megawatt. So the actual system operating state, we don't know that. And we can use a DC model and use the phase angle and the power to calculate those. Now, to solve this problem, we have 3 meters. One is between line 1 and 2, one between line 1 and 3, between these two generators. This is between the generator and one between line 2 and 3, between this generator and this load. And moreover, we have X12 and X13. The measurements from these 3 meters are the only information we have. Actually, these 3 measurements of line flows are redundant. With only 2 measurements, we can calculate the system estimate state. So assume we have the measurements of line 1-3 and line 3-2. So 1-3, if you go back, is 5 megawatts, and 3-2 is 40 megawatts. But to be able to calculate that, we have to convert it to per unit. So if we assume that per unit is based on 100 megawatts, we're going to have 5 divided by 100 gives us 0.05 per unit for M13. And the same, if we have 40 megawatts here, divided by 100 gives us 0.4 per unit. So again, the number that we got here, this is actually, we divided by 100, so we would have 5 divided by the 100, then we would have 0.05 per unit that we have per unit. And the same for the 40 megawatts. Now, to solve this problem, we had the same thing in the previous lecture as well. We can use these equations. First, we would assume the measurements of line 1 and 2, and 1 to 2 and 3 to 2 are perfect without error. So we can solve it for M13 as P13, which is equal to theta 1 minus theta 3 over X13. And M32 is P32, theta 3 minus theta 2 over X32. We have to assume one of the bus is the reference bus. Here we would assume theta 3. We can assume any of them to be the reference bus. And the reference bus theta phase angle is going to be equal to 0. Then we solve the above two equations. P13 or M13 is already known, which is 0.05 per unit, and M32 is 0.4 per unit, and theta 3 is 0, theta 1 is unknown, and X13 is, from here you can see it's 0.4. And from this, theta 1, which is 0.02 radians, and theta 2, which is negative 0.1 radians. Then we can calculate line flow on line 1 and 2. So P12, we already have theta 1, we already have theta 2, and we have X12 gives us 60 megawatts. Now, so from example 1, we get that the perfect number, the actual number, which are 60 megawatts, 40 megawatts, and 5 megawatts. So 5 megawatts, 40 megawatts, and 60 megawatts. But what happens if we have a small error? So imagine that we have the measurements have a small error, slight error. So instead of measuring 60 megawatts, M12 is measuring 62 megawatts. And M13 is measuring 6 megawatts. And M32 is measuring 37 megawatts. So a slight error from the original values, which are 60, 40, and 5. So again, since we only need the 2 line flows are needed to solve this problem, we can try using M13 and M32. And again, we can use the equations. M13 is P13, theta 1 minus theta 3 over X13. And M32 is P32, theta 3 minus theta 2, X32. We would assume that bus 3 is a reference bus, therefore theta 3 is equal to 0. Then we would solve these two equations. Again, we have X12 and X13 and X23 from the previous one. X12, X13, and X23 on the left bottom corner here. Let me actually copy this here as well. And solving these equations, theta 1 gives us 0.024 radians, and theta 2 gives us 0.0925. So you can see there's a slight difference between the ideal situation and one with a small error. Then calculate the line flow on line 1, 2, and gives us 58.25. And we see here that the calculated is slightly different than the measured value. And this gives us actually the error. The reason that we have the error, if we have an ideal situation, the amount of power that it's actually produced by the generator must be the same as the one that it's consumed. And we have to have a total power. The power generation and the power consumption should be equal. So when we change some of these and have an error, it spins the whole thing out of balance, and we're gonna have error. It has a cascading effect on the system, and sometimes it gets very complicated. We need some statistical methods to be able to calculate these errors, and actually it's an estimation most of the time, and we want to keep it that estimation in a acceptable range. So now let's solve another example of the measurements. And instead of having M1 and M3 with a small error, we want to change the numbers again. And instead of calculating the previous one, we calculated M13 and M32. Now, what about if we use M12? So instead of M13, we want to use M12 and M32. So we're going to change the equation. Again, we're going to keep theta 3 as the reference bus, but instead of using M13 and M32, we want to use M12 and M32. Instead of using these two, now we're using these two to be able to calculate M13 or P13. So then solve the above two equations. Theta 1 gives us 0.0315 and theta 2 gives us negative 0.0925. And when we calculate that, P13 gives us 0.07, or in other words, M13 gives us 7.87, which is different again, 0.7. So depends on which way we look at this, we're going to get different answer for each of these. And therefore, this method is not going to work. We need to use another method. So, and this is the example that we have, fourth example. We assume the measurements with the slight errors. M12 is 62, M13 is 6 megawatts, and M32 is 37 megawatts. Can we use all three measurements to solve it? No, it's infeasible. We need a better procedure to use the information from all three measurements and meters. That's the reason we need a state estimation to be able to calculate these. So state estimation is a procedure to calculate the value of unknown state variables. Can we obtain the exact value of an unknown variable? No, never. Measurements are inexact. What can be done is to find the best estimate of the unknown state variables given the available measurements. The process is based on statistical criteria, including the maximum likelihood criterion, the weighted least squares criterion, and the minimum variance criterion. So what we need to do is to find the random measurement error. The measurements are not perfect and are assumed to have error as mentioned. This error is denoted by eta. Then we have z means is equal to z true plus eta. The random number error eta serves to model the uncertainty in the measurements. If the measurement error is unbiased, the probability distribution function or PDF of eta can be chosen as a normal, which is Gaussian distribution with zero means. So we can estimate this, and we can actually estimate it as a Gaussian function error, which has a mean, and also the Gaussian distribution and the standard deviations. So how can we find the minimum of the least square errors? We can find the estimation problem. It could be formulated in a weighted least square form. Minimum of Jx could be the sigma of I to nm, zi mean minus fix square over sigma I square. X is the state variable vector. Fi is a function that is used to calculate the value being measured by the ith measurement. Sigma I square is the variance of the ith measurement. Jx, the measurement residual. And we have the nm, which is the number of independent measurements, and ix is the measured quantity, and zi means is the ith measured quantity. So for DC state estimation, the state estimation in a weighted least square form, minimum of J theta. If we use that, when measurement of Z means is line active power flow, Pij, then F theta would be theta I minus theta J over Xij, which is Pij. And sigma square is sigma square of MWij. So we have no measurements for voltage magnitudes or reactive power flows. For DC model, if I theta is linear and J theta becomes quadratic quadratic. This means the gradient of j theta becomes linear, and thus the gradient on x of j theta is equal to 0 can be solved directly without iterations. So this is how we solve them. We have the linear function f theta, which is f1 theta, f2 theta, and so on. We showed with h of theta. And H is an m by ns matrix containing the coefficients of f theta. Nm is the number of measurements, and ns is the number of known state variable. And when we calculate j theta, it's going to be z mean minus f theta r inverse z means minus f theta. And we have j theta from this equation over here. Now, the final equation that we have, the gradient of j theta would be equal to negative 2h transpose r inverse z means plus 2h transpose r inverse z means h. Then if we calculate the gradient of j theta, we get the estimated theta. The theta estimate is going to be h transpose r inverse h, all the inverse h transpose r inverse z means when nm is greater than ns. So let's solve this example again. We would assume that measurements have a slight error. M12 is 62 megawatts, M13 is 6, and M32 is 37. X12 is 0.2, X13 is 0.4, and X32 is 0.25. And let's try the new procedure. And again, we have the equations for M12, 13, and 132. Now, using this, the new method, the number of measurements in M is 3. The number of unknown state variables is 2. So theta estimate is theta 1 estimate and theta 2 estimate, which is H transpose R inverse H. All of that inverse H transpose R inverse Z means. Now, P1, P12, P13, P32, if X12 is 0.2 gives us theta 1 minus theta 2 over 0.2, or 5 theta 1 minus 5 theta 2. Same thing for X13, which is 0.4, gives us 2.1 theta 1. And since theta 3 is our reference, it's going to be equal to 0. And again, so 2.5 theta 1 and negative 4 theta 2. And if we have the H matrix, it's going to be 5, negative 5, 2.50, and 0, negative 4. We have to find H transpose to be able to find this. And R is the sigma of M12, sigma M13, and sigma M32. Sigma, which is our error, is 1%. So 10 in the power of negative 4, 10 in the power of negative 4, 10 in the power of negative 4. And the means, Z means, is going to be M12, M13, and M32, which are the measured values, which is 62, 6, and 37, or 0.62 and per unit, 0.06 and 0.37. When we calculate this estimation, the theta 1 estimate is going to be 0.028570, and theta 2 is going to be negative 0.094286. In other words, P12 is going to give us 0.614, P13 is 0.71, and P32 is 0.377. Now, we can here actually see the measurement values with the errors. And as you can see, none of the estimated line flows matches the measurements, and the sum of square of line flow mismatches is the minimal. Now, for another example, in the previous example, all the errors were the same sigma. In this one of the errors is less. It's 0.1%, but the other ones are 1%. And if we solve everything again, we can see that a slight error is going to create a difference in all the measurements. And you can see that now. Imagine we have 100 generators, 100 bus, and 100 meters, and also 10,000 loads. You can see that it becomes very complicated, and it needs a computer-aided system to be able to calculate this. And each of these have their own measurements and their own errors that have to be put into account. Some errors are minimal, we could discard. Some of them are gross and large, and we can't discard. And then we have what we call the bad data detection, and that creates a problem. It could be even a cyber attack as well sometimes. So we have to be able to find these errors, detect the errors, fix them if we have control systems on them, or sometimes actually detect bad data as well. So what is bad data and how can we detect bad data? So for a generalized state estimation, we have three components. We have the topology processor, we have the state estimator, and we have the bad data detector. We have real-time measurements coming in from the SCADA. We have the topology processing, we have the state estimation, and we have the bad data detection, which gives us a feedback to state estimation. So state estimation is solved by minimizing JX. The JX value for quality solution should be very small. When JX is small, it indicates that calculated branch flows, node injections based on the estimated state variables would closely match the measurements. The presence of a bad measurements values will cause a large JX value and a large mismatch between the calculated variables and the associated measurements. The state estimation to indicate whether a bad measurement exists, we can simply set up a threshold TJ for JX. Then we declare bad measurements are present when JX is greater than TJ, or is greater than our error. And all measurements are good when JX is less than TJ. If TJ is too small, we would get many false alarms, which is not good. And if TJ is too big, all is well, even if bad measurements were present. We're going to miss bad data. So the threshold TJ is determined by the chi-square distribution. If bad measurements are detected, then we need to identify which measurements are bad, calculate the measurements residual YI, difference between the estimate FI and the measurements ZI. Then we have to calculate the normalized measurement residual, YI normal, and measurements with absolute value of YI normal greater than 3 are considered as bad measurements. So we have the minimum here, by the way, the average is 0, and we can find YI norm using this equation, ZI minus FI estimate over sigma YI. So the state estimation flow chart is shown here with the bad data detection function. We have the start. We will run this state estimation and obtain X estimate. And then we would find J. If it's less than TJ, then we would end. If not, we would identify and remove the bad measurements and run it through to the system. Bad data detection can efficiently detect random bad measurements, but can it also detect coordinated malicious false injection, like a cybersecurity attack, which we'll explain in the next class. We will start on cybersecurity of the systems and in the state's estimation, how can we differentiate between a random error and also a cyber attack. Thank you so much. This would be it for today. Please let me know if you have any questions, and I would see you again next week.